Okay, let's go ahead and get started. Okay. Okay, here we go. All right, unit 1.2. Okay, here we go. Okay, this is from President Uchtdorf. Kind of on a Uchtdorf binge right now. I'm going through, I found out in the general conference in the library, you can go by speaker. You know that? So I started way back at it. I'm working my way forward. Anyway, but this one says, when we truly understand what it means to love as Jesus loves us, the confusion clears and our priorities align. Our walk as disciples of Christ become more joyful. Our lives take on new meaning and our relationship with our Heavenly Father becomes more profound and obedience becomes a joy rather than a burden. Okay, this is the key, okay? If you're feeling burdened, especially burdened by the things that you feel the Lord is expecting you to do, focus on this love. Okay, focus on your relationship with Heavenly Father and with Jesus Christ. That is the most important thing. It is the fundamental to everything. Okay, which is what we're going to be talking about today with our simple vibrators. This is the foundation fundamental to everything. Okay, we have two more of our TAs here today. We have Kayla and Caleb. Not to be confused. Okay. Caleb held office hours yesterday, 4 to 6 for help. Did anybody get to go? Couple people. Okay. All right. So he will be in the lab room 4 to 6 p.m. Tuesday, Thursday to help with homework / answer other questions. Kayla has office hours today at 11. I actually don't know where. So if just hang around with Kayla, we'll find a room right after this. I didn't give that a time yet. If those times don't work for you and you are sure you want to see a TA to get help, I need you to email me so we can try to find a time that works for you. Okay. All right. So you guys don't mind. Okay, these are our handouts for today. Questions, Learning Suite questions, where things are questions. Leave that. I get back into Learning Suite here. Okay, so keep your eye on these announcements. Things that are important, I will email you, but I won't email you necessarily everything because I don't want to spam you too much. Okay, under content, again, under content, I go to student view. Okay, if you click on course materials, then you can see the slides. That's the things that we are using in class. If you want to look at those before or after. Sometimes I won't go through all of these. They have lots of words on them and I like to do discussion. But if you want lots of words, definitions written out and all of those things, okay, you can find them there. And then the handouts are here. Video examples. This was me last time after class going more carefully and slowly through the number equations, the problems on the handout, if that's helpful. Class notes are what I write on my iPad during class. We'll start with just unit. And then the handout video ones is the one I make when I make the Zoom recording. Okay, so hopefully you can find those. Other questions? Yes. I will bring the handouts. Gradually, I'll figure out how many of you are using them electronically and print a better number of them, but I will plan on bringing them. Good. Other questions? Personally, I have to take notes right to stay awake whenever I sit in an audience, so hopefully that will be helpful. Okay. Anything else before we get started? Okay. If you have lab today, please go and see your TA, meet your TA. So this week's lab does not count as a point. Okay, it's just to make sure you know where to go and your TA can start next time. Okay, with regards to the homework, after 10 a.m., after it is due, you can see which ones you missed and the correct answers. You get to it through the grade book. I can't see how you do it, but you can ask one of the TAs or a fellow student if you ever want to see exactly which ones you missed and what the correct answers are. Okay. All right. What other questions do we have? Okay. Attendance is a big deal to me. No, we do not have everyone here. You're on your honor to mark your class attendance. If you are ill and cannot make it, I don't want you to come if you're ill. Just email me and then I will email you the link for the recording after class is done, and you can watch it and count attendance, okay? But then you also have 4 excused absences for all your other reasons you might miss. Periodically, if I start noticing not many people are here, I will take roll in class and compare it to what you're writing on your class attendance. So please be honest. That's not fun when I have to call people out. Okay, natural frequency. Okay, we're going to actually start this discussion going through our masses and springs, the interactive simulation that you did. And I read through a bunch of your answers and have a whole bunch of people I would like to help. Okay, so here we go. All right, so is Sarah Anderson here? Hey, Sarah, tell me about equilibrium. What's going to happen if I put this on? And we'll stop it. How do I stop there?
Equilibrium is something that is where it's just set, right?
Okay, yep, exactly. So if I have it off, okay, and I ask it, what is the equilibrium position? That is where it will just sit once you put your mass on. Okay, so I have a real live example over here. Okay, so here I have this. After it's there and it's just sitting, this line is now our equilibrium position. Thank you. Okay, next one. Let's see. Okay, Chloe Ashton, you're here? Okay, Chloe. All right, if I pull this down, it goes back up. Why? What did you say in your learning activity? What did you call it that makes it go back up from where I pulled it? Do you remember?
I think so.
No, you're good. You're good. You just used a really good word. I just wanted to make sure what we were thinking about. Okay, you think about that for a minute. Okay, is Sophia Austin here? Okay, Sophia, define oscillation for us.
Is it the up and down movement?
Right, so any movement that repeats like that will be oscillation. So we'll use the word oscillation and vibration synonymously. Okay, right? Anything that's moving like that will be an oscillation. Okay, Katie Black. Okay, tell me about period. How do you define the word period?
Period is the amount of time it takes to complete a cycle.
Exactly. Okay, that's an important one. We're going to use that one all along. Period, which we'll use as capital T, is the amount of time to complete a cycle. Okay. All right. Somebody have a stopwatch here on one of my front rows. Okay. We want to time 10 cycles. Ready? You be our timer. What's your name? Elena. Okay, here we go, Elena. Ready, set, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 5.3 seconds. Is that the period? No, that was the time for 10 cycles. So how would I find the period from that? 5.3 seconds for 10 cycles. How much is it for 1 cycle? What would I do? Multiply or divide? By 10, so I get 0.53 seconds. Okay, good. All right, now let's put this same mass on a different spring. Okay, this is its equilibrium position all the way down here, right? Okay, it stretches a different amount. Why does it stretch a different amount? What is that property that we call it? The spring stiffness is how we're going to describe it in this class. It is described numerically by a spring constant. You'll never use a spring constant. We'll just talk about stiffness, more stiffness, less stiffness. Okay. All right. So is this spring more or less stiff than this one? Less stiff. Okay. All right. Good. So do we expect it to have a longer or shorter period? Longer period. Okay. Good. Here we go. Ready? We're going to count again. It's going to be our time. Ready, set? Set, go. Start over. Move it away from the table. Okay, here we go. Ready, set, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10.8 seconds for 10 cycles. So we divide by 10 to get the period of roughly one second. Okay. That's kind of a nice number, because what is the relationship between frequency and, or the definition of frequency? Let's see, is Ashlyn Berg here? Okay, how about Madison Bushnell? Okay, all right. How about Spencer Ashworth? Okay, Spencer, tell me about frequency. How would you define frequency?
It's the number of cycles a second or a given time.
Exactly, number of cycles per second. Okay, so if this one has a period of 1 second, that's the time it takes to complete one cycle is 1 second. Then what? How many cycles did it complete in a second? 1. Okay, and if this has 0.5, which is a half a cycle every second, or half a second for a cycle, what is its frequency? 2. They're inversely related. One is the inverse of the other. Okay, we'll write that out, and it's on your handout. T, which is the period, is 1 over the frequency, or conversely, frequency is 1 over the period. Okay. They're inversely related. Our frequency will be in units of seconds. And our period, our time will be in seconds. Our frequency will be in hertz. How many of you have heard the word hertz before? Okay, that means cycles per second. Need to hold on to this idea. We're going to use it every day, or not every day, but throughout the whole class. Questions about frequency and period? Good deal. All right, let's see. Oh, here's another good word, amplitude. Let's see, is Joanna Bowers here? Hey, Joanna. Tell me about amplitude. What is the definition of amplitude? That's okay. You can say pass anytime. If your brain goes blank, you can just say pass. Okay. You were Spencer Ashworth. There's also Spencer Ashton. Are you here? Okay, Spencer Ashton. Give me a definition of amplitude. Do you know what that word means?
It's the displacement from the equilibrium, like reach.
Okay, the displacement from equilibrium of one extreme. So when I pull it down here, so I'm going to use my phone because I have your names on it. Okay, that's equilibrium. I pull it down. The amplitude is the distance between equilibrium and that maximum displacement or distance from equilibrium it's going to go. Okay, so if that's the cycle, right, it's going through that much amplitude. Now, it's a hard one to show. We'll go with this one. All right, so here is equilibrium. Pull it down, that would be the amplitude, that distance. And then it should go up and down around that. Okay, so the word amplitude I'm going to use most days in this class. So it's one to get really familiar with, and it tells us how large an oscillation is. Okay, and that's related to how much energy. Yes, please.
So is it the total or just the difference?
Just the difference from equilibrium. And what was your name? Louisa. Louisa?
So just the difference between equilibrium to the, like, where you let it go from?
Yes. So the distance from equilibrium to wherever it's located during the cycle is called displacement. But the maximum displacement is the amplitude of the oscillation. Questions about that? Okay, we're going to use that word a lot, so we can review that as well. Okay. Okay, let's see. Sam Bagley, are you here? Okay, Sam. Tell me about the relationship between different masses and the frequency at which this thing is going to vibrate.
Ooh, okay.
Okay. So for example, if I put a 1, I'll give you a visual. Okay. If I use a 200 gram mass on the same spring as if I use a 50 gram mass. That's not a good idea. Let's try this one. We'll show that. Okay, there's our 200 gram mass. And here is our, whoops, 50 gram mass. Which one has the higher frequency?
The higher mass one. Wait.
bigger mass or the smaller mass? Which one had the higher frequency?
Oh, why am I forgetting this?
That's okay. I'll let you look at it again. Frequency is the number of cycles per second.
Okay, then the lower mass one.
The lower mass has the larger mass has the lower frequency. In other words, there's an inverse relationship. So if we're looking for a frequency of a mass spring system, okay, you don't have to worry about the square root of the 2 pi. The mass goes on the bottom. The bigger the mass, the lower the frequency. And what goes on the top? What increases when it increases, the frequency increases also. Okay, Bailey Bond, are you here? Got it right. Okay, how about Boston Billies? Okay, Boston. Stiffness, okay? So mass is in the bottom, stiffness is in the top. This idea that the natural frequency that something is going to oscillate at or vibrate at, okay, is proportional to the stiffness, meaning if the stiffness increases, the frequency increases, and inversely related to the mass, meaning if the mass increases, the frequency will go down. Okay, so during the class, we're going to do a lot of these relational things. So I might say, for example, if stiffness increases, what happens to the frequency, up or down? Okay, and if mass increases, that I'll just abbreviate by m, what happens to the frequency? Oh, I gotta draw my arrow, sorry. What happens to the frequency? Yeah. Okay. So this idea is really critical in all of sound. Yes, please. It's like the rigidity. It's like how much, it's really easy for me to like stretch this string. And it's harder for me to stretch. I have to apply more force to stretch this one. And then this one is like super stiff. Okay. So if I put, I can get them to behave. If I can put 200-gram masses on all of them, they'll all roughly rest around equilibrium. If I get them to stop. Okay. All right. Now I'm going to try to get them all going at once so you can see which string is stiffest. Which spring is stiffest. Okay, so if you were told these 3 springs have the same mass, which spring is the stiffest? Which one is it? Your left, right, or middle? Middle. Okay, because the frequency is the highest, meaning the period is the shortest. Okay, all right. Now this may seem maybe like we're just playing with masses and springs, but this concept actually is critical to an amazing number of physical systems and sound. Yes, what's
So
your
Olivia,
okay.
so the thickness of the spring doesn't necessarily mean stiffness, so that's more of a concept, but it can impact stiffness.
Yeah, so often thicker springs are more stiff, but that would be only if they were made of the same material. Because they could be made of a different material and not be thicker, but be stiffer. That makes sense. So if they're the same material, then a thicker string would be stiffer.
This is a concept. It's how thick the spring is, the spring is.
Yes, so the spring stiffness is related to the thickness and the density and some of those and some other material properties, but we'll just summarize it as stiff. Okay, good comment. Yes, please.
Was the stiffness related to the length of the springs?
Oh, great question. Is the stiffness related to the length of the springs? Like, for example, if I took this one and cut it in half, so that it like when it had no masses on it, it was the same length. Would it change that stiffness, that natural frequency? No. It's a material property of the spring itself.
Great, so it's just.
Yes, it is only, yes. Yes. The fact that this is the longest and this is the shortest is not relevant. Thank you for clarifying that.
So this how tightly it's pulled?
No. I think how tightly they look coiled is dependent on how much they've been stretched out over the years. But that's also good observation. Okay, good. Okay, let's see, what's next? Set my- All right, so next, damping. Samantha Barahona. Are you here today? Hi, Samantha. Tell me something about, you observed about damping in this simulation.
I pass.
Yes, you may pass. Okay, all right. Anybody else want to help us on damping? I will give us a visual while you're getting brave, while you're thinking. Okay, we talked last time about how you can reduce friction, right, by adding air. Right? Okay, so here's another way to look at all of this. If I set this to oscillate, right, meaning going back and forth, it has again a certain period of motion, the amount of time it takes to go there and back. It has a certain amplitude, which is the largest it's displaced from equilibrium on either side. Okay. What is going to happen if I make it now more massive by adding more mass? Higher or lower frequency? Lower frequency. You see the difference? Okay, good. All right, now that went quite a long time, right? With about the same amplitude, the same maximum displacement. Okay, and I'll go back to this one so you can see it. Okay, and now if I put on my flag here, it's like adding damping, right? Air resistance is another kind of friction damping. Okay. Okay. And that basically takes some energy out of the system. And then if I turn off the air, so regular friction now acts as damping. Gonna go forever? Okay. So damping removes energy from the system.
With damping, kind of do the same that friction was for the kinetic energy.
Yes, so on the skater app that you did, that the friction was a form of damping.
Okay.
Mhm. Or, yeah, damping is anything that takes energy out of the system, and very often friction is what it's doing. Some kind of friction, yes.
Is damping the same thing as resistance?
Ooh, good question. She asked if damping is the same thing as resistance, and the answer is yes. Okay. Okay, I guess I should actually get one of the handouts, shouldn't I? Did we have any extras? See how we're doing. Okay. All right. Go ahead and pull out your ABC apps or cards. Okay, if you're new to class, I forgot to bring them today, but typically on your phone, you can get this ABCD app that has A is red, colors are on the announcement. Okay. And then put it somewhere easy to find. It'll look like this. Yes, please.
So, whenever there's energy from the system, does that mean that it's being converted to some other type of energy such as heat? Or is it
Yes.
completely-
It is turning it into the thermal energy that we talked about the other day.
Okay. But not really.
The total energy of this, of like the system, if you include the heat, stays constant.
Okay.
But the useful energy that can help the oscillation continue goes down. Okay, good. Okay. All right, let's just quick go through the front side of this. Okay, all right, how we on? Everybody ready? Okay, number one, true or false? The frequency is the number of cycles in 1 second. Be fast. Written on the board. So just to make sure you have your app out and ready to go. Okay, good, true. Okay, does a 300 hertz tone or a 900 hertz tone have a longer period? Go ahead and think about it, but then I need everybody to give me an answer. And if you don't know, just choose. Okay, good. Let's go through this because I see about half and half. And if you don't know, please just do something so I know you're with me, okay? All right. The frequency, wrong one. I'm gonna just leave the cap on. Okay, for frequency equal to 300 hertz. Okay, the period is going to be 1 over that frequency, or 1 over 300 hertz. Okay, which will be approximately, if you did that on your calculator, 0.3 milliseconds. Okay, now if we have 900 hertz. Oh, what is milli? 3 decimal places, or sorry, 3 milliseconds. Okay, and frequency 900 hertz, then the period is going to be 1 over that frequency, or 1 over 900 hertz. Okay, which is going to be approximately 0.1 seconds. This little squiggle, 2 squiggles means approximately. Okay, so you can do those on your calculator and find that. Okay, so, but in general, if the frequency is higher, the period is lower. They are inversely related. Okay. Yes, please.
I just wanted to correct, it should be like 1 millisecond.
Oh, yes, yes, yes. I got my zeros wrong. Thank you. 1, it should be a third, right? So 1. Approximately, if you round. Thank you. Okay, good. Other questions? Okay,
Can you put the board back up to what you agree?
okay. All right. So number 3, what is the period of a 500 hertz tone? Okay. What do you think it's going to be? I'll give you a hint. 500 is between 300 and 900. Show me your answer. Okay, the answer is D. Let's write it out. Okay, the frequency is 500 hertz. And the period is 1 over 500 hertz. Which if you do 1 divided by 500 on your calculator, I don't expect you to do these in your head, okay? I just chose numbers I can kind of work with. Okay, then it would be 2 milliseconds.
Just to clarify, this is a class so like use a calculator like on the test.
Yes, you may use your calculator on the test. For sure, and on your homework. About halfway through, I'll teach you how to use your log button. So we can talk about decimals. Yes. It will not. It will not be big. It won't be tricky in any way. It'll be very obvious. Okay, good. All right. Any other questions about that idea of natural frequency and period? Yes, please. So the natural frequency is the frequency at which something naturally wants to oscillate or vibrate. Okay, now let's look at number 4. If you double the mass on the spring, will the frequency increase or decrease? Okay. Throw me up an A or B. Let's see, everybody participate, please. Faster we do it. A or B? All right, good. The answer is B. Okay. Consider 2 springs, one stiffer than the other. If the same mass is used on each one, which will have the longer period of oscillation? The looser one or the stiffer one? You can think about the timing. that Elena did for us over here? Was it the looser or the stiffer spring that had the longer period? Okay, good. The answer is A. Questions about those first topics? Yes, please.
What is the relationship between resistance and frequency?
There is none. Okay, it's a trick. Okay, so resistance just, well, for our class, there's none. In practice, things that are moving very fast tend to counter more resistance. But for the level we're going to talk about, it's just resistance is taking energy out of the system. It is damping. Damping and resistance can be synonymous for our class. Okay. So, but the resistance does change the decay rate of the oscillator. Many of you observed this in your learning activity, that the more resistance there was, the faster it stopped, right? So that would be the decay rate would get smaller as there's more resistance. And you can think of that even just in terms of, okay, if I took something like this water bottle and I slid it across the table, right? It stops, right? I'll do it again where you can actually see it. It stops, right? Okay, that's just because of friction, that's the resistance, okay? If, for example, I come back over here and I put my, okay, and I give it some resistance, right, this is normal. Depending on how much resistance I give it, if I just barely rub it, it'll take longer. So the decay rate depends on resistance, but not the actual natural frequency.
Give it any resistance, is that going to go on forever, or is it for the air from the eventually stop it?
The air resistance, and then there's just a little bit of friction up here. So those two things would eventually stop. Good observation. Okay, good. What else? Okay, this is an interesting little video. Okay, this is going to show you how this idea of the mass on a spring can look like a sine wave. We're going to represent it as a sine wave, but it's just going up and down, right? It's like not moving sideways. But this is the visual you need to have in your head when I start drawing these kind of pictures for the displacement, like is on the back of the handout. Okay, that's the displacement of the spring, how far it is from equilibrium as a function of time. It's only going straight up and down, but I'm scrolling my paper past it to keep a record of the displacement versus time. Okay, questions about that? It's a pretty cool demo, huh? Or visual. Okay. All right. Did you want to see it again, or do you got it in your brain? How this picture, this displacement picture here relates to our springs. Questions about that? Okay. We're going to use that idea lots of times. That one. Last year we had to make videos of all these demos because we were online. So I'm very glad we're not. Okay, now energy. Okay. I'm going to draw on the board that same picture that we just saw representing the displacement of the spring on the mass as a function of time. So first I'm going to pull it down and it's going to go like this. Okay. Pretend it's a sinusoid. This is the amplitude of the wave, right? Either that number there or this number here. One's positive, one's negative. But the maximum displacement from equilibrium. So if it's lower than equilibrium, I'm going to give it a negative to start. Then it'll come through equilibrium and up to its maximum displacement at the top, and through equilibrium down to its lowest, etc. Okay. All right, now I'm going to give some letters for these guys. For us to do a little bit of, oh, I didn't do the I didn't read the prompt, so I'm gonna start over. Did I do it right? I'm gonna let you do it. Okay. All right. Okay, so on your graph there, put circles where the potential energy is the greatest, meaning it's stored energy, and X's where the kinetic energy is the greatest. Okay, and that Tim there should really be timed. Okay. So in our mass spring system, where does it have the most potential energy and the most kinetic energy? In other words, where is it going the fastest? Actually, I think maybe you can see better on this one. Okay, now notice, how fast is it going when it reaches one end? Right, that's the big question here. How fast is this going at each end when the amplitude, the displacement is the maximum? Does it have a speed at that point? It actually has to stop for an instant, right? Because it's going this way, and then it has to go that way, down and then up. And the only way to make that change is to go through zero. So there's that instant when it's maximum amplitude where it has zero speed. How much is the kinetic energy when you have zero speed? Zero. Okay. All right. How you feeling like you're doing on your zeros and your X's? Okay. All right. Now I'm going to label them. Okay. And we'll do your little okay. All right. At which point is there maximum kinetic energy? There's more than one, but you can just choose either of them. Okay. Maximum kinetic energy means it's moving the fastest. Okay. Go ahead and show me an answer. Got a row back here where hardly anybody's showing me answers. Come on. I'm not strict when it's simple. I'm going to lose you completely by the time it's hard. Okay. All right, good. A or C. Okay, so those are where the X's should go. Potential energy is the maximum in both of these places. It is the same potential energy, same amount of potential energy. Okay. All right, questions about that? Okay. We'll revisit that idea. But okay, about on the pendulum. Where do you think so in the case of the spring that we just did here, the mass spring system, this was the potential energy is spring potential energy. It's stored in the spring, the elasticity of the spring. That restoring force, that was the word that someone had on their learning activity. That was a good word, restoring force, right? So in that restoring force, the elasticity of the spring is where that potential energy is stored. Okay. For a pendulum, it's gravitational potential energy like we talked about with the skater. Okay. So just to review this one with the pendulum, one that's shown up here on the left, where will the potential energy be the greatest for the pendulum? A, B, C, D, E. E, if it's ever an E, you just turn your phone sideways. Okay. Good. Yes, A is the answer. A or E. Okay. Questions on this? We're going through a lot of fundamental ideas that are going to lay the foundation for our understanding sound in more complex systems. Any questions? Okay, then we're going to talk about resonance, which is a super important topic in sound. Sometimes it's really good, and sometimes it's not good. Okay, resonance is the idea that things, when they are pushed at their natural frequency, get very large amplitudes to their oscillations. Okay, so consider pumping a swing, right? You sit on a swing, you lean back, you lean forward, lean back, lean forward. You could measure the period of that oscillation. You could determine the frequency of that oscillation. If you're getting a large amplitude on your swing, then your period of of moving your body is matching the natural frequency of the swing. Too many English in this class. Swing. That makes sense? Have you ever tried it where you just like do your legs really fast? Maybe when you were little. Do you get a large amplitude? No. Okay, because you're not driving it, you're not pushing it at its natural frequency. Yes.
Kind of
maybe,
the same
right?
idea as a seesaw, like you can't push when the other person's pushing, otherwise neither of you will go anywhere.
Yes, you have to have that nice addition of energy, the push at the right times, once every period. Okay, so whether you're swinging or that. Okay, so this is a little demo, okay, where I have my mass on my spring, but now it's being driven. There's a little gear down here that's driving it. Okay, and it's holding the swing up and down, up and down, up and down. Okay, so sometimes it has large amplitudes, relatively large, and sometimes it has smallish, and it's not regular, okay? This is the case when something is not being driven or pushed at its natural frequency. Okay, this is not resonance. But if I tune the driving frequency, the pushing frequency, so that it is closer to the natural frequency, then I get a nice large amplitude, right? That, oh, and it's not quite exact because it's almost there, but not quite. It should never go to zero if I'm exactly at resonance. Okay, just like you pushing a swing. You don't, if you missed it and did it like half a cycle earlier or something, you would mess up your motion, right? So that's the idea of resonance. Okay, so let's give some examples in sound of where resonance is good. Okay, who has an answer for me? Think about it. Where is resonance a good thing? Yes, please tell me your name.
Well, in like singing, you want a lot of resonance and clear that the sound kind of like rings.
Exactly. In singing, right? How many people have had actual like singing lessons in our? Okay, good. So is how you hold your mouth important in singing? And the difference between like a belting voice and a choir voice. Is your mouth different when you sing? Okay, that is resonance. Okay, you're changing the cavity of your mouth to have different resonance or natural frequencies, what we'll call formants when we get to speech, to give the tone color you want, to accentuate certain frequencies. Give it either a brighter tone or a mellower tone. Okay, very good. Other examples? Yes, please.
I know when I sing in the shower, like there are certain places in the shower that will like be really loud, like close to your corner or something.
Exactly.
It's fun to like find those.
Find the loud places in your shower. Okay, that is resonance. Rooms have resonances, natural frequencies at which the vibrations really, if you sing them, if you drive them at those frequencies, you get big, loud amplitudes. Okay, in the back. And then you.
Would tuning an instrument be considered resonance?
Yes, because those, like if you're doing a string instrument or a wind instrument, you're modifying either the length of the wind instrument or the tension of the string to make it so that that natural frequency is where you want it. But then the bowing has to match, right? The stick slip of the bowing has to match the frequency you want to drive. Otherwise, you get the beginner squeaky sound.
So back when I used to be in bands, snare drums have what are called snares at the bottom of the drum that create like a nice sound. But whenever the wind instruments played a certain tone, the drum would resonate and create a horrible vibration sound. So you'd have to pull off the snares.
Very true. Okay, but you can have other sounds that cause a resonance on something else that you didn't want the resonance on, right? Or if you play a certain note on a piano really loudly, other strings will vibrate sympathetically if you wish. But it's because that vibration that you started is matching some resonance there. Okay, over here. Yeah.
So like how you have like a glass and then you can put your finger in water and
That is exactly resonance. Okay? So you are trying to, with the stick slip motion of your finger, stick slip, match that driving force to the resonance of the glass. Exactly. Yeah, over.
Well, when you're trying to break a glass, you're trying to get to its natural.
Exactly. Yep, yes,
Is that like overtones too? Is that
overtones.
like when it matches? Or
Yeah, that's a little more complicated, overtones, but yeah, we'll save that a little for when we get more to the singing voice. But, okay, as was just mentioned, if you want to break a glass,
By breaking a glass beaker with
Okay.
a sound wave. This beaker.
you
has
can
a
do it with your
natural
voice too. This one just looks a little bit
used
more
by
fancy.
gently tapping its brim.
That's the natural frequency.
We create a resonance by exposing the beaker to a sound wave of the same frequency. For this demonstration, we use a stable oscillator or amplifier and a horn driver which controls the
so
signal.
that's the
emitted
signal.
by the beaker, so that both the amplitude.
That's the
increase
amplitude's
and
larger,
phase
right?
shift can be observed above.
Okay, and now it starts to vibrate. This is under a strobe. You couldn't see this actually with your just regular eyes. Okay,
Until the oscillation of the beaker exceeds its elastic limit.
so that is an example of resonance to make sound, but too much resonance sometimes is a bad thing. Okay. All right, let me show you some more examples. I showed you that example. Okay, bottles can be resonators. Okay, if I blow on this bottle, right, then I get a really low resonant frequency.
So when he was holding the beaker, he had it like this. Where he holds it, will that change the frequency?
That's a good question. So you can damp the oscillations in some parts and force there to be nodal lines there. Like when you, or if you're playing a harmonic on a guitar or a string instrument, and you just lightly touch the middle, it doesn't sound the same anymore because you've killed mode one, which we'll talk about.
But like the way he was holding it, like it didn't change the frequency needed to make it oscillate.
Okay, here is a bad example of resonance. I'm going to turn the sound off. Oops, sorry. I wanted to just turn the sound off, but I got it. Okay. Just turn the sound down. See if that works. Okay, so they're just doing some test of the rotors, but one of the rates of rotation, darn it. Sorry. One of the rates of rotation, come on, matches a physical resonance of the system. And if you leave it there long enough, the amplitude overcomes the strength of the forces holding it together. Okay, so that can be a bad thing. This is a Tacoma Narrows Bridge. If you ever take a physics class, you have to watch a little bit of this one, right? Okay.
Tacoma Bridge, Washington,
We're not gonna
opened only
watch
a
all
few
of it.
months ago with built cost of over 6 million.
Okay, but it has these lovely oscillations. And the wind, and the wind one day drove it so well in oscillation, its resonances.
Fortunately, the only pattern.
So that's a bad example of resonance. Okay, so this is last but not least, this is actually my dad flying the F-117, that black one shaped like a triangle, right? Okay, back before the world knew it existed. Okay, when we didn't know what he did except go on Mondays and come home on Thursdays, he was a test pilot for this plane in Nevada. And then one day he came home and said, "Oh, I got a medal." Like, hey, what? Who knows? Okay, and then he leaves and is like, gets this weird plaque that has like these just random pieces of metal on it. And like, yeah, okay, whatever. And then a few years later, the first picture comes out of the plane. And then he could tell us this story, why he got the medal for bringing this plane in. And it's all to do with resonance. Okay, so he's up on a test flight, not testing the tails, testing something else. But he does something that causes the tails to be driven at resonance. And one of them disintegrates. And then he goes through the motions he needs to make sure the other one doesn't and is able to land. Okay, it happens really fast. That's why I'm telling you at first. It's grainy. It was one of the chase plane footage, but this is an example of resonance. When something is driven at resonance that you don't want it to have driven. So it has two tails. The back one, the one farther from you, is the one that will go. See it start to move. It could be gone that fast. Okay, so resonance is extremely powerful, and resonance again is when there is a driving force, some kind of push that matches the natural frequency of a system. So when people are designing things, when mechanical engineers are designing things, they have to be very aware of resonances, right? And be very cautious of that. Okay, we're going to use these ideas of period frequencies, masses and springs, resonances throughout our whole class, okay? So take time to make sure you've got a good foundation in these. If you want to talk to Kayla now about homework, just come up here and we'll find a good place. Okay. Let me know if you have any questions. Yeah.